Processing experimental X-ray absorption spectra is important for being able to properly analyze the data. The main processing steps include normalizing the data and also extracting the chi of k oscillations from the absorption mu of e data. These steps are not too difficult, but some care should be taken when doing these steps. Hi, I'm Matt Newville, a beamline scientist with the Center for Advanced Radiation Sources at the University of Chicago, where I run an X-ray microprobe beamline for X-ray absorption and fluorescence spectroscopies. This presentation is part of the video series on the fundamentals of X-ray absorption fine structure and is also part of the virtual summer school at the Illinois Institute of Technology and Advanced Photon Source at Argonne National Lab. In this video, I'll go over some of the data processing steps for XAFS. Again, these include normalizing the XAFS spectrum, which is used for all XANES analysis, and for the extended XAFS, it also includes the background subtraction to isolate chi of k. Fourier transforms are also vitally important for understanding XAFS, and so we'll also go over many of the features of Fourier transforms for XAFS analysis. The steps shown here can all be done with several X-ray absorption analysis programs including sixpack and athena and the XAS Viewer application that is part of the Larch package. So the steps for processing the data, again, to get mu of e and then even chi of k, are to convert the measured intensities from our ion chambers and detectors to mu of e. Then we'll subtract a smooth pre-edge function, removing any instrumental backgrounds or absorption from other edges. Then we'll also normalize the data so that mu goes from about 0 to about 1, so that the mu of e represents the absorption of the average element of interest, and that allows us to compare data measured on different samples of different concentrations and different sample measurement modalities, transmission of fluorescence, for example. For analyzing the XAFS, extended XAFS data, we'll also remove a smooth post-edge background function to approximate mu of e 0 or mu 0 of e to isolate the XAFS chi, where that's the differential absorption, the measured absorption minus an idealized atomic background. We'll also need to identify the energy threshold E0 so that we can convert from X-ray energy to photoelectron wave number k. And we'll also then talk about weighting the chi of k and doing Fourier transforms to get us from k to R space. And after we get the XAFS chi of k, then we can model the data with FEF calculations or do a similar analysis on the extended XAFS. So the XAS Viewer is part of the Larch package and it provides GUIs for processing beamline data to chi of k and can do all the steps that I'll show you here. Again, there are many other programs that can do this, including Athena and sixpack, which are also excellent at doing these steps. So we'll have collected XAFS spectra mu of e. This is already partially reduced, of course, to give our mu of e spectra. Then we'll convert that to chi of k, doing background subtraction, and then do Fourier transforms on that. So the data processing features of XAS Viewer and actually Athena and sixpack have almost all of these features as well, or all of them, or with some differences, is that they can do data visualization and read in raw data and do merging of data and merging of multi-element detector data and so on. They can do the pre-edge subtraction, find E0, and normalize the spectra, and then they can do the background subtraction all pretty much in the same way to get chi of k. They'll also be able to help you do Fourier transforms, and then you can also reread data and save them into projects and so on. For XANES analysis, all of these programs, I believe, include some XANES analysis that might include pre-edge peak fitting, linear combination analysis, and principal component analysis to identify how many different components would be in the XANES spectra. There's also several sorts of data corrections that might be necessary, including deglitching or energy realignment, correcting for overabsorption of fluorescence data, and you may need to smooth a rebin or deconvolve data from in the energy space. And all of these programs can do some of these. I won't go over the data correction steps too much. There are online videos showing some of those available in XAS Viewer. Here's some just screenshots. Again, this is just to show that it's a GUI and you can get different plots and there are forms for doing all of these steps. It doesn't require much in the way of serious attention to programming or anything to be able to do these steps, although those are all possible too. So let's start with turning the measured intensities the real signals that we measured into mu of e. So for transmission XAFS data, which is the way you would measure data for high concentration samples, typically above 5 weight% or so, we want a mu that looks like this, that has a step that is positive and goes and increases with energy in electron volts. And so we have a transmission chamber, maybe downstream of our sample, that would measure a signal like this, a loss of intensity as the absorption goes up, and then an I0 channel that probably decays somewhat with energy and might have some small glitches in it. And then we can convert those two measured intensities into our mu0 just by taking the negative log of the ratio of the two measurements. For fluorescence data, the situation can be slightly more complicated. Actually, in some ways, it's easier. Mu we'll just say, is proportional to some emission channel fluorescence IF over I0. That could come from many different sources. There may be many different detectors. So there may be multi-element detectors, as is shown here, where multiple channels are measuring the fluorescence simultaneously. Still, we want to construct mu0. That's now just IF over I0. And here's our I0 again decaying, and the sum of these channels divided by I0 will give this mu0. I should say that you need to make sure that you get the right one, that you don't mix up processing fluorescence data as minus the natural log or transmission data as just I over IT. And typically the standards or very high concentration samples will be measured in transmission, and low concentration samples will be measured in fluorescence. And I say fluorescence here, but it could be other emission modalities, electron yield, visible light spectrum, and it also includes high resolution fluorescence or HRFD kinds of analysis. So all of those are emission and would be constructed in the same way. Yes. So we will need to, or it's often the case that you'll need to, real data will include several different scans of data, and these may need to be merged. So that's just adding spectra together, although you may need to think about doing some interpolation if the energy scale is changing from a monochromator that has some problem, or the monochromator energy might drift in time. And so you may need to select and align data or use a reference channel to measure a spectrum either at the same time or in between, or alternate between measuring a metal foil, say, or some stable oxide phase and the elements of or the samples of interest. And that could be done at the same time, or every other scan or something, or once a day, or possibly once a week, depending on the energy stability of your beam line. And then at certain energies, there might be glitches in the data. These are understood that they come from extra diffraction peaks from the monochromator, and they may not normalize out well from the mu of v. If they don't normalize out, you should consult your beamline scientist for why they're not normalizing out better, but they may not normalize out perfectly, and they may need to be just removed as spurious measurements of the absorption. It usually is not a disaster to remove a few points from any spectra. We tend to oversample mu of v to get chi of k well. But then for concentrated samples measured in fluorescence, there is this feature of overabsorption that I won't go into much detail here. It is written up about, and you may need to correct for that. And that can be corrected knowing the stoichiometry of your sample and having some transmission data, even if it's noisier than the fluorescence data, can be useful. Again, XAS Viewer and sixpack and Athena can help with all of these steps, including overabsorption, and are relatively easy to use for these processing, for these data corrections. So the data reduction from our measure of mu of e. Once we have mu of e measured in transmission or fluorescence, and we've already done some corrections on it, we want to get then, the first step is to get normalized data. So it goes from about 0 to about 1 above the edge. It'll never be perfect, and we're looking for getting this to a few percent level or so. There's sort of two ways I'm going to show to do this. The classic way shown first is to fit a line to the pre-edge region, and then also fit a curve, possibly a line or possibly a higher order polynomial, well above the edge, and then extrapolate those to the edge, actually to E0, which I'll discuss in a second. And then the difference between those is the edge step. So here it's about, the edge step up for this spectra is about 1.2 or something. In this way, we use the spectra itself and no other knowledge to fit simple line shapes and determine the edge step. The pre-edge comes from all the other edges below and from instrumental artifacts. Once we get the normalized data divided by the edge step, then we can use this for any XANES analysis or for any subsequent analysis that we want to use, either for XANES or for extended XAFS. And I won't go into the XANES analysis features. There are demos and discussions of that in other videos in this series, in this related series. So the XANES spectra, just near the edge, around 100 volts around the edge, will show very rich structures, which are highly dependent on oxidation state and on local chemical environment. We'll use the derivative spectra to identify E0. So we're trying to identify here the absorption threshold. So the first derivative is often used because it's easy to do. It's not correct. It's not where the absorption threshold is. Actually, the absorption threshold is way down here. It's where the absorption starts. And you can argue about which energy levels are included in that, and so where the main edge is. But we'll typically use, and we'll avoid that conversation for now, and typically use the maximum of the first derivative, mostly because it's easy to do and easy to reproduce and easy to explain what you've done for that step. And it's also usually not too far off. In fact, it usually puts it a little bit higher up the edge than the actual threshold. But for using calculations, say from FEF, that's actually the right bias to have for E0, is to pick the sort of higher energy. Again, we'll keep this in mind. We'll need to refine this as we go, but this sets our scale for K, the wave number, when we're doing extended XAFS. And we'll just let that go because it's easy to do. There is another way to normalize the data. Instead of using a linear fit to the pre-edge and some polynomial to the post-edge, and that's to use tabulated values of mu of e. These values for mu of e, not including XAFS, are tabulated at the atomic level, say from Chandler et al. There's other tables that could be used. So we could use this. We could use this sort of known shape where it does drop as e to the -3 with energy, and the edge shape is sorted, or the edge position is known reasonably well. So you could say, let's normalize by making a few adjustments so that our raw data matches or our measured mu of e matches the tabulated mu values from the tables. This can be a good approach because it really improves consistency. The same functional form is used for all spectra of an edge and element, and the post-edge these polynomials don't go kind of crazy, veering off unexpectedly. So here's the two compared for this data set. The difference is usually at the level of where it's hard to tell which one is correct and which one is a little bit worse. So here's this MBAC. It's labeled as MBAC here after the program by C.C. Wang and Jim Penneron's group, and then this classic polynomial background. So they're both reasonable, and I would say be consistent. And if you're doing lots of data from lots of different sources, try them both. And the tabulated values, the MBAC approach, might be slightly more consistent over data sets, and so easier to make consistent. Okay, I'll not try to scroll too far ahead. So again, that gets us our normalized XAFS data or normalized XANES that we would use for any analysis. To get the extended XAFS, we'll need to do post-edge background subtraction, where we're going to model a smooth function. We'll call mu of e, that is meant to represent the isolated XAFS the isolated absorption of an atom without its neighbors. We don't have a measurement of that. In fact, a gas wouldn't be quite right, theoretically. We need the response of the atom embedded in the molecule or in the solid, but not with any scattering from the neighbors. That's hard to manufacture such a sample, although a liquid or a glass can be a good start. But so instead of trying to do that, we model it with a spline. A spline is just a mathematical function, a piecewise continuous set of polynomials, and we will use that to make an adjustable spline function. So a spline is meant to fit anything. So this can be quite dangerous, and it could match mu of e and remove all the XAFS, and we don't want that. We want a spline that is the low frequency components of mu. I'll come back to that in a second. Once we've isolated chi, we've subtracted mu from our mu0 and divided by our edge step, our normalization, we have the normalized chi of e. And that looks like this. There's a huge spike in one direction or the other at the origin, and then the oscillations die out in energy. So we'll typically convert from energy space to wave number space, k, which is the square root of the energy and then the mass of the electron and Planck's constant to give k in inverse angstroms. So then here you can see the oscillations are spread out. It's square root, so 10 is about 300 electron volts, and you can see that these oscillations here at very low energy are spread out now more in k. That's still, we don't see any oscillations out very far out, past 10 angstroms or so. So it's typical then to also multiply chi of k by a power of k, either k or k squared or k cubed. So if we multiply by k squared, then we'll have the XAFS, and we'll see all of the oscillations continuing out to k of 12 or so for this data set. This is sort of realistic data, not pristine or perfect. So again, we emphasize the higher k portion of the spectrum by multiplying by k squared or k cubed, sometimes k to the first power. You'll see many of those in the literature. And again, the main features are to try to get the oscillations to be about the equal size throughout the range, so that you can see the oscillations and you can see where the noise level is at high k, and then to be consistent and just use the same k weighting for all the data analysis you do, or to play with it purposefully and know that you're playing with it. So as we can see from these plots of the k-weighted chi data, chi of k is composed of sine waves. So we'll Fourier transform the data to R space. And indeed, Fourier transforming XAFS data is what really allowed the initial understanding of XAFS data to be understood. And so to avoid truncation problems or ripple in the XAFS, we'll also multiply by a windowing function. Here's a very smooth type of windowing function that is commonly used. So we'll multiply the blue curve times the red curve and then do a Fourier transform. When we do that, we get a Fourier transform that looks like this. We've now converted to R space, and we have intensities that correspond approximately, pretty close to the different shells of atoms surrounding the central atom. So this data is for iron oxide. So this is the iron oxygen, and this is the iron-iron peak. The peaks here are not at the actual distances. There's a phase shift that's discussed in more theoretical talks and will be shown in demonstrations of analysis as well. There's a phase shift that's due to the scattering phase shift, So this is a Fourier transform that's really of 2kr plus delta k. In addition, we've done the Fourier transform where we plotted a function that's positive definite, the magnitude of the Fourier transform. But the Fourier transform is complex. And usually only the amplitude is shown like this, but actually the data has these oscillations in it. And when we do any analysis with the data, we're going to analyze the real and imaginary components, not simply the magnitude. So that actually means that a fit that might look like it's not perfect in the amplitude is actually very good in the real or imaginary parts. So we need to use both of those in modeling the data. It's common, especially in the older literature, you'll see this. It's common then to try to isolate a single shell of a chi of k spectra, or chi of r spectra, to isolate a shell and get the isolated oscillations from just one shell of atoms. To do that, we can do another Fourier transform, back from r to k, often called a back Fourier transform, or sometimes called transforming from r to q space, or back transform k space. Here we've done this, we've isolated this one portion of the spectrum that looks like an isolated peak. It's pretty good for this data set. It's not perfect, but it's pretty good. And when we do that, we get isolated oscillations that look like this, that correspond pretty well to the iron-oxygen scattering isolated for this data set. So now that we've seen the basic procedures let's go a little bit into more detail on background subtraction and Fourier transforms, and then we'll be able to do XAFS analysis. So for background subtraction, we know this is where we're going to choose the spline to use as mu0. We know that a spline is a smooth adjustable function, a piecewise continuous polynomial, and fitting this can be dangerous because it can be flexible enough to remove all the XAFs. So Athena and XAFS and all of these programs choose a background spline for mu0 that minimizes the low R, the low frequency components of chi of k. So spline parameters for mu0 are guessed. So the spline is guessed, and then a Fourier transform is done from a spline is guessed, that gives a chi of k. A Fourier transform is done, and then the spline parameters are adjusted until chi of r below some RBK, some distance, R background, RBKG, is minimized. The portions of the spectra above RBKG are completely ignored, but the portions of the spectra below RBKG are tried to be minimized. So the most important parameters for this method are RBKG, the distance below which chi of r is reduced, and then the k weighting of the Fourier transform, and then the energy origin, or E0, that we picked for our data. And I'll go over the effect of a few of these, but not of E0. So again, we're going to try to reduce as much as possible the low R components of our Fourier transform. So here's the effect of RBKG on this real XAFS data. So if we pick RBKG of 1, I'll say that's a decent default value for lots of spectra. 1 is the default choice in these programs, and it's actually a good choice for lots and lots of spectra. It's rare to have atoms that are closer than about 1.5 angstroms in real solids. It happens, but it's rare. So if we picked an RBKG value of 0.3, that's not quite flexible enough. And you can see that there's some low frequency oscillations in the blue curve that don't show up in the red curve. And if we look at that in Fourier transform space, actually this should be with 0.3. And so through that, those are 0.3. We have this peak at low R when we used RBKG of 0.3, compared to which is a stiff spline, compared to a more flexible spline with RBKG of trying to remove the components below 1 angstrom. And you can see we tried to remove the components below 1 angstrom, and it did a pretty good job of removing most of the low R components when we asked for that. So the rules of thumb for doing this are use a RBKG of about 1 angstrom. If you have short distances, you might lower that to half the near neighbor distance. Lowering it to 0.75 or so is usually not a problem. And then also don't spend too much time on background subtraction. Let's get on with it and analyze the data. In fact, you can see from this that even though we did sort of a very stiff spline, it doesn't make very much difference in the further out portions of the spectra. There's some slight changes here but this portion of the spectra above about 1 angstrom is pretty unaffected by getting the background a little bit wrong. So it's an error on the side of being too low rather than being too high. Because if we make that too big, then we have a much bigger problem. So if we here the green curve, it's a little hard to see with this, I suppose, that in this space, but we see some oscillations there. But those are pretty different, and it might be difficult for you to tell from that alone that there's a problem with the data here that has RBKG of 2. But if you look at that in Fourier space, you can see that it actually tried to remove and did a pretty good job of removing all the low frequency components up to now 2 angstroms, and it's completely removed our first shell XAFS. So we still have these higher shells that are important. That's the iron. Those are important parts of the scattering, but we've completely lost the first shell, which might be a problem for really analyzing the data well. So again, having RBKG too big is the most important thing to avoid. You want it to be 1 angstrom or less, and it's better to be on the small side than on the high side for RBKG. So to do that analysis, we did Fourier transforms, and I should, you may want to revisit this after watching this portion of the video, because I should, just to make sure that you understand Fourier transforms well. So Fourier transforms are vital in understanding XAFS analysis. We take our data, chi of k, and we multiply it by a window function, and we also k-weight it, and then we do this transform, which is the Fourier transform, to get chi of r, our Fourier transform of the XAFS. We really use a discrete Fourier transform, of course, because we're using data that's been digitized. It doesn't make much difference, really. Although we put the data onto chi of k, when we convert from our raw data into energy space, we put the data into a uniform k grid with a spacing of 0.05 inverse angstroms. And then we fill the data past the real data range out to about 100 inverse angstroms past the edge. That sort of smooths out the data a bit in the Fourier transform. The data then in our space is on a grid with a spacing of 0.03 angstroms, and can go out to 30 angstroms, which is ridiculously far. And in other videos, we might discuss why we want to look at the data past, say, 10 inverse angstroms, even though there's likely no data out there. So a Fourier transform takes an oscillatory function, and we're going to use a window function, so we'll multiply it by this sort of window function. So here's some data that I totally manufactured that has a distance of about 1.6 angstroms and a sigma squared of 0.003. Just so that's a decaying sine wave. Actually, there's no photoelectron pieces in this data. It's just a decaying sine wave. And when we Fourier transform that for with an R of 1.6, we get a peak that's at about 1.6. So we get some breadth to the peak. That's because we have a non-infinite number of sine waves that we've included, including partly from this sigma squared value. If we look at a few different Fourier transform, a few different oscillatory functions, so here's sine wave with R of 1.6 angstroms and a cosine wave with R of 1.6, so that's just a phase shift range. They look just out of phase. A sine function with an R distance for 2.3 angstroms has a higher frequency of oscillation. Higher frequency means further distance. So that high frequency oscillation, there's more oscillations in 10 inverse angstroms, and so that pushes the peak in R space out. So that's now peak. These two now peak at 1.6 angstroms, and this peaks at 2.3 angstroms. In fact, you can't really tell from this plot by itself of the magnitudes that what the phase is, that there's a difference in phase between these two. They look the same, but they're not. They're completely out of phase. So the Fourier transform is complex, and if we take those sine waves and do Fourier transforms and look at not at just the magnitude, but the real portion of the Fourier transform, you can see that it's a bit messier, but you can see that the blue and the red curve are very different. In fact, they're actually nearly completely out of phase, that's what the effect of being 90 degrees out of phase is. That the peaks where the red curve is high, the blue curve is 0, and where the blue curve is high, the red curve is 0. waves with slightly different frequencies can cancel each other by causing beats. This is a common occurrence in all frequency analysis, so you'll hear it in music as well, where you have two oscillations that are close to each other in frequency. They'll start off in phase, but eventually they'll get out of phase and then get completely out of phase and then continue on with a little bit of oscillation. And when we add those two together, it decays much faster. There's a place where it's nearly zero, and then it starts to grow again. And when we Fourier transform those two, there's a slight, these are waves with distances of 2.3 and 2.4 angstroms. So the blue curve is 2.3, 2.4, it's shifted a little bit, and the sum of them is actually smaller because it's more reduced by this effect. So the amplitude itself of the Fourier transform does not necessarily give an indication of the weight of the oscillation fully. It also includes this effect of if there's weighting or if there's reduction from these two, from this disorder that's added to the spectra. So I guess what I'm trying to say is that these two adding together give the blue and the red curve adding together give the green curve, not something that's twice as big. So mapping height of this peak onto coordination number is challenging because it also includes this disorder term, this decay term. When we Fourier transform, we multiply by window functions. And I just picked one for all of the Fourier transforms that I showed you so far, but there are a great number available, and you'll see the different ones in the literature on Fourier transforms, and especially in the XAFS literature. They all go from about 0 to about, at the far ends, to about 1 in the center, and some of them go up and stay at 1 for a long time, and some of them are just smooth. And some of them have different functional forms for this portion, the window sill, if you will, or the edge, or the actually often called the foot, or the apodization of the window curve. The most important thing to keep in mind is just to be consistent. My personal recommendation would be use the Kaiser-Bessel window of a decay of about 4, as that is just, it's never wrong. It does reduce the data somewhat and emphasizes the middle portion of the spectrum, but it's often just the easiest one to use because you don't have to mess around with trying to figure out other portions of the spectrum, other portions of the window function. So for the window functions that use a K-min, a K-max, and a delta K value, a dk value, they look like this. So this is a Hanning window. It goes as cosine squared up from centered at K-min and with a width, a total width that's the dk value. And then it'll stay at 1 until K-max minus half of dk, and then drop down to 0 at K-max plus dk over 2. So that's the meaning of K-min, K-max, and dk for all of these window functions. Well, all the window functions that drop from 1 to 0, all of these window functions, Pars and Hanning and Welch, are all pretty similar. They just differ in the functional form used, whether it's linear, cosine squared, or k squared for how it drops. And there's lots of discussions in the Fourier transform literature on which of these is better. It sort of doesn't matter much for XAFS data at all. Again, consistency is the most important thing. These are all available. So those are all available, but including a windowsill can be useful. Using 0 is not such a great idea. So here I show window functions with 0, dk of 0, dk of 3, and 6 for the Hanning window. And you can see that there's these little ripple that's just artifacts of incomplete truncation of oscillations. It's actually not too bad, and the differences between these are not too different, but they're different enough that you want to be careful about, again, being consistent and picking values that aren't too unreasonable. If we just use different window functions, but use the same dk value, then we see differences like this, which are all pretty minor. There isn't much difference. You might see a little bit of difference in here, a little bit of difference in how this spreads out. The Kaiser window is a little bit suppressed and so on because its average value is a little bit lower. And the most noticeable thing is that the ringing of the small peaks changes a little bit, but not too much. And again, I think the Kaiser window is probably your your safest bet as the default. So there is also, I'd like to show you, before we go too far, the effect of k-weighting on the Fourier transform. So in the Fourier transform, we do k-weighting. We multiply the spectra by k to the w. And again, this is iron oxygen. So there's iron oxygen here and iron here. And if I use a k-weighting of 0, I get this sort of spectra. These are all rescaled then. K-weighting of 1, k-weighting of 2, and k-weighting of 3. And you can see that for k-weighting of 0, where I've emphasized the low k portion of the spectra, the oxygen peak is much higher, or the oxygen peak is pretty high compared to the iron peak. Whereas if I use k-weighting of 3, the oxygen peak is about half of the iron peak. And so that's because low W values, low weighting values, will emphasize the high K and so high Z scatterers, which scatter at higher K. High Z scatterers scatter at higher K values. So again, K weighting of 2 and 3 are most common and recommended, although 1 is not uncommon. Finally, for Fourier transforms, I think K-min and K-max are also important. So you can also make a similar effect on what the relative weight of oxygen and iron are in this spectra by changing K-min. So if I set K-min to 0, I get this spectra. There's some little ripple. It's probably not great. K-min of 2, it doesn't look too noticeably different. But if I go to K-min of 4 or 6, that oxygen peak here is also really changing and being suppressed. And again, that's because oxygen scatters at low K much more than iron does, and doesn't scatter at high K, say above K of 10 or so. There's hardly any iron oxygen scattering. So again, using a K-min of about 2 or 3 is probably a good idea. Going to K-min of 0 is a bit challenging because the model of using extended XAFS at low K is somewhat specious or not very good to say that the XAFS actually continues and can be modeled as a sum of paths below about 2 inverse angstroms. That's really the XANES region. We can start there. We're not emphasizing it much if we're doing K weighting, but we want to make sure that we're not too far into the XANES range of the data. Finally, I just want to show you that we've looked at Fourier transforms, and it's fundamental to understanding XAFS, but wavelet transforms extend the Fourier transform by mixing K and R space. And they've been used by a handful of groups for XAFS analysis and can be pretty illuminating in understanding the nature of the XAFS and highlighting the different phases that I showed here by changing K-min and by changing the K weighting. And in XAS Viewer and Larch, you can do these transforms readily, and you can even do the analysis in wavelet space. So here we've made a map where effectively we have K on the horizontal axis here and R in the vertical axis. So features that again, this peak here is the iron oxygen peak. And it decays relatively rapidly. So by about K of 8 or so, it's pretty small, whereas the iron peak continues to scatter a little bit further out in K. And so this map is also the same representation of the data. Here's another view of it in 3 dimensions. And these can be very useful for understanding data. And then the fascinating differences in the spectra out in this range are also worth looking at. So I think I've gone way over my hoped for time on this video. So the conclusions for XAFS processing are that XAFS processing, although I talked about it quite a bit, should not be too difficult. And the main takeaways are don't overthink it and be consistent. And for there's more information on X-rays and X-ray absorption spectroscopy at all of these links. And if you have any questions, comments, or concerns about this video or suggestions for more videos or changing content, leave them in the comments below or let me know. Thanks.